Hello everyone. So we will be starting off with part 4 of the video lecture series on context-free grammar. And here we will, as I have already mentioned in the first introduction lecture, where I have explained to you what are the topics we are going to cover. And in the part 4, we'll be covering today the topic context-free grammar and context-free language. Then we will talk about ambiguity property of a grammar with an example. And we will check it out two numericals where we have to write a CFG, that is context-free grammar, from a language and from a regular expression. So this is the agenda for this particular video. Now let us start off with the first topic where I am going to let you know. Till now we have understood about regular grammar, where you came to know that a grammar is denoted by a capital letter G with four tuples V, Vn, Vt, S and P, right? Or in some books they used to write as V as Vn, T as Vt, and S and P. Okay, so don't get confused. These are all the types of representation. So so now we will look into context-free language and context-free grammar definition. So if we talk about context-free grammar and regular grammar, the definitions are both same. Only lies between a small difference in the production rule. So that I will let you know now. Okay, now what is context-free language? You can pause the video and you can note it down the definitions and whatever stuff I've mentioned over here. So context-free language is nothing but a context-free language is a language generated by a context-free grammar. So main focus where we have to give is context-free grammar. So they are generally more general and include of regular language. Okay. So what is the meaning of this? I will let you know once we will jump off to the context-free grammars. Okay. So if I ask you how to find out a context-free language, then the main question comes in your mind is that you have to first generate the grammar, or you have to first generate the context-free grammar. And based on the context-free grammar only, you are able to find out the language, which we'll be going to implement today. Okay. So now let us move to the topic, that is context-free grammar. Mathematically, the context-free grammar is also denoted by capital letter G as compared to regular grammar with the same four tuples. Either you can mention as Vn, Vt, P and S, or else you can mention as Vn, then T, capital letter T, P and S. It depends upon you, whatever you are comfortable with. Okay. Now it's said to be context free if, as I mentioned you, that we need these tuples where Vn is nothing but the set of non-terminals generally represented by capital letters. I have given you a shortcut notifications earlier as well. T or Vt, here I have mentioned over here. T or Vt is nothing but the finite set of terminal symbols. Generally, apart from Vn, whatever symbols are present in the grammar will be your Vt. Then S is the start symbol, that is nothing but the starting non-terminal. Okay, and S always belongs to capital letter Vn. Okay, and last is P. P is nothing but your set of production rules, which is of the form you already know, alpha tends to beta. Now here a small difference lies where the right hand side, that is beta, is same as compared to Vt and union Vn whole to the power star. But in alpha, in terms of regular language, if regular grammar, if I ask you, alpha belongs to at least alpha should have at least one non-terminal, whereas here in context-free grammar, alpha always belongs to exactly one Vn. That means we are not concentrating on that is at least one Vn. Okay, exactly one Vn there should be. So this is the small difference between regular grammar and a context-free grammar. Okay, so this is the definition about context-free grammar, which like you should know about. Rest everything, the question will be coming across grammar CFG, a grammar G. So don't get confused. We will be working on the same process. Just context-free grammar and regular grammar, if you want to identify, you have to identify on the small difference which lies in the production rule, which is also in the left-hand side, that is alpha. Okay. Now, finally, we can conclude by saying that the family of regular language is always a proper subset of the family of context-free grammar. Okay. So if someone asks you about this particular thing, then you should have the formal description of both regular language and context-free language. Okay. Now this is about your first topic where we have learned about context-free language and context-free grammar. Now we are jumping off to the next topic where we are going to learn a property of CFG, which is known as ambiguous grammar or ambiguity property. Okay, let us check what the property is all about. Okay, so this is the definition of ambiguous property, ambiguous grammar. Okay, what does ambiguous grammar says? CFG is called ambiguous if for at least one word in the language that it generates, there are two possible derivations of the word that correspond to two different syntax trees. Okay, that means primarily I have to focus on two different syntax trees, correct? And one more thing that I have to take in consideration is two possible derivation and two different syntax trees. If these two scenarios are successful for a particular CFG, then that CFG is said to be ambiguous grammar. Otherwise, it is called as unambiguous. So generally, 2 marks question is very frequent if you are attempting for any university exam paper. And there generally comes, what do you mean by ambiguous grammar? What is the property called ambiguity? So this is a frequent question. Okay, so you can mark it as an important one. Okay, now let us move to the example where you will be able to understand what is these two possible derivations, what is these two different syntax trees. Okay, the example says here, for the grammar G, G is given by this one, that is your start symbol, capital letter S, then A, comma B, comma plus and asterisk, and then S and P. So these are nothing but VN, VT, S and P, correct? Now where P is given by these production rules. Now we have to find out that the string can be generated or not. Okay, so that can be generated, I think so. So let us check it out how to generate this particular scenario. Okay. Okay, so first of all, I will check it out. What are the productions I am having? I am having the productions S tends to S plus S and S asterisk S and A and B. You can also write in a same line, or you can also write S tends to S plus S tends to S into S tends to A, S tends to B. That depends on you. Okay. Now we have to find out the string A plus A into B. So what I'm going to do, I am going to introduce two different terms today in this particular scenario. And these two important topics we will be discussing as a part of definition in part number 5 of the video lecture. Okay, so first one is your leftmost derivation. Leftmost derivation. Okay, in leftmost derivation, what we are going to check, I will let you know. First, we will be taking the production. Now here your logic applies. You have to find out A plus A into B, correct? So for that, I have to take the production through which I can go with the leftmost derivation. Leftmost derivation says that if you're taking a production like this, suppose, okay, let me take this, S tends to S plus S. Leftmost derivation says that you have to eliminate the non-terminal symbols from the left-hand side until you reach the right-hand side. And rightmost derivation, what it says, the next one that I'm going to discuss with you all, that you have to eliminate from the right-hand side until you reach the left-hand side. That's it. Got the difference? So let me check. I have to find out A plus A into B. Now suppose I'm bringing out a logic. Suppose if I eliminate leftmost derivation, definitely I have to eliminate this, correct? So if I eliminate this by, suppose, A, okay, then A plus S, yes, again I can eliminate this by S into S. So here the logic goes correct. So I can eliminate this S by, in the next step, you can also write down like this. That depends on you. So, or you can write in the same line. Okay, and you can write it down, LD. Okay, LD means leftmost derivation. So S I am representing, I am using by A plus capital letter S. So now what I have to do, only one non-terminal symbol is there, so definitely I have to eliminate this. Again in the next step, LD S. How you are going to represent? I am going to eliminate by using this S cross S asterisk S. So A plus S asterisk S, correct? So this is what the leftmost derivation is all about. Now we are going on the same track, correct track. Now which non-terminal you are going to eliminate now according to leftmost? The leftmost one non-terminal. So I will eliminate this, and by using LD, what will be the value that I am going to replace by S? Definitely S for the production, small letter A, because A plus A. So A plus A into capital letter S, and finally I have to eliminate this. So the by which terminal symbol you are going to eliminate? S tends to B, and finally you got the string that you want. So this is how you have derived by using leftmost derivation. But as I've told you, according to the definition, what it says that to two different syntax trees, so we have to concentrate on the tree also. So the derivation tree will be, so what will be the derivation tree? As I've already told you about derivation tree in the previous lecture. If anyone has skipped it, then please go to my previous lecture where you can check it out, the definition of derivation or parse tree. Okay, so now derivation tree, how I'm going to start off? I'm going to start off the same process. Okay, how? First, again I'm telling you, the root node is always the start symbol. So as I'm representing this, the first one, I'm removing this. So S implies S plus S. Okay, now you have to keep in mind that only the non-terminals will be encircled. Apart from terminal symbols will remain as it is. Okay, now next, what you did in the next one, you did S, the left hand side S I have eliminated by using A. So I will be replacing this by A, correct? Then next what you did, A plus S. Again I have replaced S by S cross S asterisk S. So I will replace this by S asterisk S, correct? And then finally again I have replaced the leftmost S by which symbol? By A. And then finally this one I have replaced by P. Therefore the derivation that you got is, the string that you got is A plus A into P. So this is how you did the leftmost derivation. Now what I'm going to do with the ambiguous grammar is that I will be now checking the rightmost derivation. How? The same process, rightmost derivation. So in rightmost derivation, I'm going to check S implies. Now what we are going to take now, the logic comes over here. Which grammar you want to take, which production you want to take first. I'm having two productions, S plus S and S asterisk S. I have to check the right side of the grammar, correct? So what I can do, I can take the second production, suppose, okay, and S cross S. Okay, this is the second thing I have taken. Now I have to go with the right side, correct? So RD, so right side is this one, so I have to eliminate by, now after asterisk, what is the symbol, what is the element you want? B, correct? So S cross B will be the one. Now what is the left out one non-terminal? S. So again I'm going to replace it by, now which production you are going to use? S plus S, correct? So the production will be S plus S into B. Again I can use right derivation. If I use right derivation, then what will be the answer? Which one you have to eliminate? The rightmost S. If I eliminate this rightmost S, which production you are going to use? S tends to A. So the production will be S plus A asterisk B. And then finally I have to replace only this S by which production you are going to use. You have to use the S tends to A. Therefore, the final string that you got is A plus A cross B. Done. And then I am left out with the last step, that is your derivation tree for the rightmost derivation. So I will draw the rightmost derivation tree a little bit fast. S, then you got S into S. Then what did you do with the last S? You just replace it by B, and then here you did S plus S. Then you replace this one first by using A, and then you replace by this one. So if you check it out from the left hand side, the string that you got is A plus A into B. Now the question arises that whether this grammar is ambiguous or not. So if you check properly, I have derived this string A plus A into B, and for twice with the help of two different structured syntax tree. Correct? Both the structured are different. That means if such case arises, then that particular grammar is known as ambiguous grammar. Suppose if you are deriving the same string and the structure is same, then you are not supposed to say that that particular grammar is an ambiguous grammar. That will be called as an unambiguous grammar. So understood? So the final definition that I can say from this particular grammar is that G is ambiguous. Correct. G is ambiguous. So this is what all about ambiguous definition, ambiguous property definition. So if any doubt, please pause the video and check the steps one after another, and you will be able to understand very nicely. But only the point that you have to remember again and again is that for the same string, if you are getting two different structured syntax tree, then that grammar is called as ambiguous grammar. So by the end of our entire video lectures of third unit, I will give you 25 to 30 questions where this ambiguous grammar question will also be there. Okay. So now we are left out with last topic, where we'll be going through the two examples, and those two examples will be on writing a CFG from a language and from a regular expression. Okay, so let us check out what kind of questions are there. Okay, so we are having this topic named as numericals based on writing a CFG from a language. Okay, so these questions that I have brought on behalf of your pattern based questions, and now here you will be able to understand how to write a CFG when a language is given to you. Okay, so let us start off with the first question. The first question says that write a CFG which generates strings having equal number of A's and B's. Correct? So if they are asking equal number of A's and B's, definitely I have to first I have to assume that CFG B, capital letter G. So I have assumed that the CFG is capital letter G, and G is defined by how many tuples? 4 tuples, VN, VT, S and P. Correct? So this is my assumption. So I have taken as let. Okay. Now, as you told that in your exam you can write it down what VN stands for, what VT stands for, what S and P stands for. But here what we have to find out, we have to find out only the production rule. Okay. Now, as I have told you that you have to find out equal number of A's and equal number of B's. So I can write it down like this, that A to the power M and B to the power M, suppose. Okay. Now, this can be of like the initial string that I'm going to find out is AB, equal number of A and equal number of B. I can also write it down A, B, B. Correct? I'm finding out the possible strings. Then I will be jumping off to the grammar. Okay. That it may be triple A, triple B. Okay. It may be, maybe B may be starting. So B, A. Correct? It may be B, B, A, A. It may be triple B, triple A. It may be AB, AB. It may be AB, AB, AB. Correct? So these are the possible strings that I have find out. If you are having any more strings, then you can also write it down, but I find it okay. So these possible strings will be there. Now we have to check it out, what kind of grammar that we can make it out. Correct? So I'll be taking only one non-terminal. So VN I will be taking as, suppose, capital letter S. This is my logic. Once you do with like 2 to 3 numericals, then it will be easy to understand how this logic you can apply. Okay. Now suppose, and VT I have taken as you know, A and B will be your VT. And if suppose you might be requiring epsilon also, that is a different one. So I won't be considering right now. Okay. So next is your start symbol. So S is your start symbol. Okay. And now what is your aim? Productions. Okay. So I can write like this. S tends to A, S, B, S. This is my logic. If S tends to epsilon, suppose S tends to epsilon. Now here epsilon comes, so I can remove this part, and I can also include in terminal symbols. Correct? So S, if I apply S as epsilon, then if I apply here, then it will be AB, which is the first one. Now if I want the second one, AABB. So if I repeat it again in terms of S, suppose I'm writing over here. Suppose I write it down, S tends to AS, BS. I'm replacing this S by again the same production, A, S, B, S, then BS. And then again I'm replacing this S by epsilon. Then what will be the string? AA, BB. So which is the next string? Which is the next string? Then again, if you want triple A, triple B, again you can replace it by S by the same string. Correct? In this way, you can go n number of times until you are satisfied. And once you are satisfied and you want to stop the process, you can use this production, S tends to epsilon. Correct? Now we are done with all these three things. Now suppose if the string is BA, so I can take one more production as BS, AS, the same way. And S is already epsilon, I have told you. So finally, if you want BA, this is correct. If you want BBAA, again the same process that we did in here. Correct? So this will also be correct. Now if I want ABAB, this also I can do. In this, I will take this first production, and in place of S, I will implement this production, and then you will get ABAB. So finally, checking all the conditions, I can say that these productions are perfectly fine. So therefore, the grammar will be, therefore the CFG will be, non-terminal will be capital letter S. What will be the terminal symbols? A, B, epsilon. It depends on you if you want to write the epsilon or not. That is not mandatory. Then what will be the start symbol?